All right, sir. We've started recording, sir. So you can use the whiteboard. We've provided for a whiteboard if you want, and yeah,
So if I go to the whiteboard, what happens to my window for sharing?
you can also share. You can also
Okay.
share the
So
whiteboard.
okay, let me
Everything.
try to share. Um, let me see if
So
I can share. Oh,
I've approved you
oh,
as
the
a host as
sharing.
well. Yes.
Okay. Okay. Um, okay.
Maybe just an
Okay.
appeal to the
Yeah.
guys.
So
There are guys who are sending requests for approvals. Until I have a list so that I see who is on that list, then I can authorize and approve the recordings. For now, I think let's allow the lecturer to, okay, let's allow the recording to be done by myself so that we agree the way forward. Because the names, I've not yet known the actual names of people who paid up. So I'm declining to approve for recording by everybody.
okay. Yeah. Last week we ended on this example. So I tried to run it through, but I realized I think it was too fast. So I thought I should come and start from here so that we see how you can because when you look at this example is incorporating all the three laws, okay, the Kirchhoff's as well as Ohm's law, because it's asking us to determine the currents I1, I2, I3, and the voltages V1, V2, V3. Okay. But for us to be able to get those, then it would mean we have to use, I think, all the three laws simultaneously. Okay. So if we look at this circuit, uh, the currents have already been assigned to us. We can see we have I1 there, I2, I3. The voltages are also V1, V2, V3. Gap B. Okay, we have loop one, this other side, and we have loop two on the other, on the right most side. Okay, so what we are going to do is, when I start talking KVL, we'll be referring to these loops. So please take note of the loops so that when we start saying loop one, you don't get lost to where we are referring to that. Okay, so I had drawn that circuit as the one that is shown here. So to quickly run through this same example and see how the answers were obtained when you start going through by yourself. Okay, so on the left here, we said that we have loop one. On the right, we have loop two. Okay, the direction of the arrow is the direction that we are going to take when we are considering KVL. Okay, so the voltages that have because we've seen that at a node or at a certain junction, we have the currents I1 going in and I'm trying to refer to this one here. So meaning at that node, we can write the KCL. Okay, we remember we are said that you can assume, you can take your own assumption, but I like to take the assumption that the currents that are entering a node or a boundary are positive. The ones that are leaving that boundary or node are negative. So if that's the case, then I can say I1 minus I2 minus I3 is equal to 0. Okay, from there, I can quickly say, okay, I1 okay. Ohm's law states that would be equal to 8 I1. Okay, V2 is equal to 3 I2, and V3 should be equal to 6 I3. That's from Ohm's law. Okay, but still, we can't solve the way it is. We have, I think, how many presents out we have? We have the one from KCL and those expressions for the voltages. We still can't determine anything from them. Okay, so it brings us now to try and write a KVL expressions in each loop for each loop, and then see how we can try to determine which parameter or which quantity will for the currents and the voltages. Okay, so the KVL expression, you have to go loop by loop. Okay, for one loop, you get one equation, and for the other loop, you get another equation from that. Okay, so KVL in loop 1 dictates that if we start following the direction we are going up like that, it will be negative 30, okay, plus V1 plus V2 will be equal to 0, okay, meaning V1 plus V2 is equal to 30, okay, that's for loop 1. In loop 2, we are saying that negative V2, okay, plus V3 is equal to 0. Are we together up to that point? Hello?
Yes, sir. But
Right.
for the second group, where have you started with negative V2?
Have you seen the way the polarities for V2 are given? It's negative here, it's positive there, okay? And our direction of taking the KVL is clockwise. So clockwise means you are going up like this. Remember, we said that the polarity of the voltage is determined by the polarity of the terminal encountered first.
Yes, sir.
Which is the same as we did for the 30. We said negative 30. We said negative 30 because the terminal we encounter first there is negative terminal. The positive terminal is up there. So even as when you go to loop 2, the terminal we encounter first on V2 is negative terminal. And then when we go around, as we go around like that, on V3, we encounter the positive first. That's why we are saying negative V2 plus V3 equal to 0. Is that okay?
Yes, sir.
Okay. So now that we have the KVL, we can substitute the Ohm's law expressions into this KVL for the voltages. If we do that, then it means we know what V1 is. It's 8 I1, okay, plus 3 I2 is equal to 30. On the other side, you get negative 6. Sorry, not negative 6, but is it negative 3? Okay, we have negative 3 I2 plus 6 I3 being equal to 0. Okay, so now we have three equations. We have this one here and this one, okay, and also the one from the KCL. Because here, when you look at the ones, the expressions from KVL, the two expressions, they have two parameters, two unknowns. I1, the first one has I1 and I2. The other one has I2 and I3. So meaning the way they are, it's not easy for you to solve. If not, you cannot even solve them. So because remember, you have to have the same number of unknowns and the same unknowns. Okay. But when you look at the two, the only one that is common between the two is I2. How are you going to get I1 and or I3? So what you have to do is now you substitute for the KCL, okay, into the equations that we obtained from KVL of loop 1, so that we can have the same unknowns as the ones that we obtained from loop 2. So if we did that, then we'll have 8 bracket I2 plus I3, okay, plus 3 I2 equal to 30. So meaning if we did that, then I think this one should go to 11 I2 plus 8 I3 is equal to 30. Okay, and then you can see that now this expression that we have gotten now has two unknowns, I2, I3, and also the ones that we have loop 2, it also has two unknowns, which is I2 and I3. That means that these two equations can now be solved for the current I2 and I3. So how you would solve that, I think we already know. Okay, you can use any method that you can remember in order for you to determine what I2 and I3 is. Okay, others they opt for the matrix, you can use elimination, substitution, or any way that you can remember from the previous years that we've been in school. Okay, so I can write by myself. I like to use, I think, depending on the complexity of the equation. So this is I2 plus I3, I2 plus 8I3 is equal to 30. Okay, so this is 11I2 plus 8I3 equal to 30. And then I have negative 3I2 plus 6I3 is equal to 0. So for me, this one, I like to use elimination. So I want to eliminate I2 from these two expressions. Okay, so what I'll do is I'll multiply by 11 down and multiply by 3 up. Okay, and then the resulting equations, I should be able to add them. So if I do that, then the one on top will give me 33 I2 plus 24 I3 is equal to 90. The one below will give me negative 33 I2 plus 66 I3 equal to 0. So the fact that I have 33 I2 and negative 33 I2, if I added these two equations, you realize that this one will cancel with that, and then I'll remain with that is 66 plus 24, I think should be 90 I3 equal to 90, meaning I3 is equal to 1 amp, like that. Okay, I've obtained 1 amp. So I can pick now, since I know what I3 is, I can get what I2 is from using any of those original equations that, or any of the two equations that we already know. Okay, so I can still say negative 3i2 plus 6i3 should be equal to 0. If I do that, then I know to say i3 should be equal to 3 times 1 over 6. This would give me 0.5 amps. Okay. Now, since I know, oh, sorry, not, I'm solving for, sorry, not I3, but I'm solving for I2 here. So instead of saying, well, the way it is there, then it's supposed to be, this is I2 that we don't know. Okay. It is 6 times 1 over 3, which gives us 2 amps. Okay. So now we have I2 and I3. From KCL, we were told that I1 is I2 plus I3. Therefore, I1 is equal to 2 plus 1, which gives us 3 amps. Okay? And now the fact that you have all the currents, okay, I1, I2, I3, you can go back to your Ohm's law expressions now to determine what those voltages are. Okay? This is equal to 8 multiplied by 3, which gives us 24 volts as V1. V2 was 3I2, which is equal to 3 times 2, I think was equal to give us 60 volts. And therefore, V3 also will be equal to 6. I3 equal to 6 times 1, which is 6 volts. Okay, so I think we've discussed, mentioned on when two branches are or elements are in parallel. Okay, we said that they must have the same voltage. So if you look at V2 and V3, they are the same. Okay, which should be the case, because if you look at the 3 ohm and the 6 ohm resistors, they are connected in parallel. So we expect them to have the same voltage. Okay, so in an event that you solved this and you got V2 and V3 to be different, and the circuit was as the one that is shown here, then we know that, oh, something is not right. We have to check that again. Okay, otherwise, that was for that example. You can still try to go through from the notes and see that the answers that we obtained are actually the same. This is I2, this is I1. Okay, this was I3, V1, V2, V3, respectively. Okay, unless if there's a question, we can now move on to where we should have started from today. I just wanted to go back to try and probably clarify one or two things from where I left last time. Otherwise, we are supposed to start from here. Is it a go ahead for me to start talking about the series and series resistors and voltage division? Okay. So
Yes,
series resistors and voltage division. So what we're trying to say is there will be a case or a situation where you have so many number of resistors. Let's say 100. Okay. You know the resistance of each resistor, but then they are connected in series. And then someone asks you to say, oh, can you find the voltage across the 95th resistor or the nth resistor? Okay, from those resistors that are connected in series. So if you try to close the circuit and then determine the loop current and then go and multiply that current by the resistance of that resistor, I think somewhat would have lengthened the process. Okay, so there is the shortest way you can do that is to use voltage division. Okay, so if resistors are connected in series, the equivalent resistance of n number of resistors connected in that manner, okay, is just the sum of those individual resistance. Okay, Zamutunda, I think kindly mute Samuel. Okay, so if you are given n number of resistors, like 100, 1000, or 5, the resistance that you would get, okay, Req should be equal to just the sum 2 ohms, okay, 2 ohms plus 4 ohms plus 7 ohms plus 9 ohms plus 10 ohms, like that. So in short, it's just the sum of the resistances themselves that should give you the equivalent resistance. Okay, and the equivalent resistance that you get from that, the value of that equivalent resistance should be larger than the largest resistor that you have in that series. Okay, so in general, if you are to find the resistance of the nth resistor, we have to use voltage divider rule. And if we use voltage divider rule, there will be no need of determining the current that is flowing through those resistors. Okay, so if a voltage divider has n resistors, okay, in series, R1, R2 plus R3, R4, R5, like that, they are connected in series to a source voltage V. The nth resistor or the 95th resistor will have a voltage drop determined by this equation 2.14. What this equation is telling us is that if I'm asking for the 95th voltage drop across 95th resistor, then this will be determined by the resistance of the 95th resistor divided by the equivalent resistance, okay, multiplied by the source voltage Vs. Okay, so the voltage drop across a resistor that is in series with other resistor is equal to the resistance of that resistor. You are trying to determine the voltage as the numerator divided by the equivalent resistance of all the resistors that are connected in series. Then you multiply that to by the source voltage. Okay. Otherwise, you might also have resistors that are connected in parallel. Okay. And we know that if there are resistors that are connected in parallel, the voltage across those resistors will be the same, but the current will be different. Okay, because depending on the value of its resistance, it will tell you how much current it can allow to flow. But again, what if you have 100 resistors and then someone asks you to say, can you find the current that is flowing in the resistor number 96? I think it would be tedious for you to start determining from resistor number 1. You keep going until you get there. So the fastest way you can determine the current flowing resistor number 96 for 100 resistors connected in parallel is to use what we call current divider. Okay. But for you to do that, you need again to know how to get the equivalent resistance because you need it. Okay. So the equivalent resistance of two resistors. Let's assume they're just two resistors in parallel. Okay. This one connected in parallel to this resistor. If we say that this is 3 and this is 6, then the equivalent resistance you get from these two resistors connected in parallel will be 3 times 6 over 3 plus 6. I think this should be clearly 2 ohms. Okay? That's how you get for two of them. Okay, you use this equation 2.15. Strictly for 2. Once resistors become 3, you can't say R1 times R2 times R3 over R1 plus R2 plus R3. No. Okay? So, if there are more than 2, the general equation dictates that 1 over the equivalent resistors is equal to 1 over R1 plus 1 over R2 plus all the way up to 1 over R100. Okay? So in short, the reciprocal of the equivalent resistance, okay, is equal to the reciprocal, the summation of the reciprocal of each individual resistor. Okay? So if you have 2 ohms, you have, for example, you have 2 ohms resistor, 4, 6, 10, all the way up to 100. Then what we are saying is the equivalent resistance of these resistors, 1 over Req should be equal to 1 over 2 plus 1 over 4 plus 1 over 6 plus 1 over 10 plus whatever up to 1 over R100. Okay, so when you have this, then you just determine now what is Req. So you know what to do to determine what Req is. You have again to take the reciprocal of whatever the total you get from that summation. Okay, so it is worth noting that the equivalent resistance, unlike in the series connection, where we say that the equivalent resistance is larger than the largest of those resistors that are in series. When resistors are connected in parallel, the equivalent resistance is always smaller than the smallest resistance in that parallel combination. Okay, so if you look at the previous example I gave, I have 2, 4, 6. If we assume that 2 is the smallest, when we calculate the equivalent resistance, the value we should get from here should be such that Req should be less than 2, because 2 is the smallest that we have amongst those resistors that are connected parallel. Okay, so that's what resistors connected in parallel dictates. But then here equation 2.17 just tells us, oh, if you have 5 resistors connected in parallel and yet their resistances are the same, then what you can just, to find the equivalent resistance, is just divide the resistor value divided by the number of those resistors. Okay, because they have the same value. So even when you add, it's like you just be determining trying to determine, I think, the mean or something like that. Okay, so because of, the issue of having 1 over Req being equal to 1 over R1 plus and the like that, it is convenient to use conductance, okay, rather than the resistor when dealing with resistors that are in what? That are in parallel. Okay? So, because it is like that, because we know that conductance, which is G, is equal to 1 over the resistor itself, or the resistance itself. Okay, so if you have resistors that are connected in parallel, better you convert that value of those resistances into conductance, because we know that when resistors are connected in parallel, they are conductances. To find the equivalent resistance, you have to have the conductances, you add them, because conductance you add when they're in parallel, and then you do the opposite when they are in series. So determine the conductance for each resistor that is connected in parallel, and then you just come and add to get the total conductance, because we know that if you have the total conductance, then the equivalent conductance should be equal to 1 over Req. Okay, so if you can get the equivalent conductance for the resistors connected in parallel, then when you just come and do the reverse of this, you get Req being equal to 1 over Geq, like that. Okay, so from this equation for resistances, it tells us that conductance is equal to the equivalent conductance will be equal to G1 3 plus G plus G100, where 10 by these expressions. Okay, so if you have resistors in parallel, determine their conductances using these relations, and then to get the equivalent conductance, you just add those conductances. Or sometimes someone might decide to give you a circuit whose resistor values are actual conductance, are in terms of conductance. So someone shouldn't be confused, say, but this is resistance, this is the resistance, and then now I have 2S or 2 whatever. No. At least you need to know and still remember the relationship between conductance and resistance. Okay, so from 2.18, what we get from there is that the equivalent conductance of resistors connected in parallel is the sum of their individual conductances. Okay, so to get the equivalent conductance, just add the conductance of each and every resistor that is connected in parallel. Okay, and also it follows that the equivalent conductance of n resistors in series will take the form of the equation shown in 2.19. Okay, so if resistors are connected in series, then their conductances are added in this manner here. Okay, so since we can get the equivalent resistance or equivalent conductance of those resistors that are connected in parallel, if you are to get the conductance, or I mean the current flowing in the 96th resistor, whose conductance is given as G96, okay, when those resistors are connected in parallel, okay, then what you have is that the current in the 96, okay, this is I96 resistor, conductance, okay, divided by the sum of those conductances multiplied by the source current. Okay, That's according to current divider rule. Okay? Or if you don't want to use conductances, what it tells you is that IN, okay, or the nth current of the nth resistor should be, if, for example, you have R1, R2, R3, okay, let's say you have those three resistors, then what you need to get as the numerator, if you are to use in terms of resistance, it should be the equivalent of those, of the equivalent resistance of those resistors minus the resistor that you are trying to consider itself. Okay, so in short, well, I'm saying the Req of 1 and 3 divided by the sum now, the equivalent resistance of all the three resistors multiplied by the supply current. This should be able to give you the same answer as using equation 2.20. Yes? Shula? Come again? I don't know if our colleague is talking, but I can't get anything from them. Shula? Okay, I guess you can ask whenever you can again, so as we can continue. But when you are able to, unless I'm the only one who can't get him, who can't get them, but yeah, when network allows, I think you can raise your concern again. Okay, so here is an example, example 2.9. It's asking us to find Req for the circuit shown in this figure. Okay, when we look from the left, okay, if we look here, what do we see as the equivalent resistance, okay, between these two terminals, A and what? And B. Or if you got a multimeter and connected at the terminals at A and B, what resistance are you going to see? Okay, so determining the equivalent resistance, you choose which side. Of course, you have to start from the far side from where you are looking at it from. So since we are looking at it from the points A, B, to determine the equivalent resistance, we have to start from this side, going to the left. Okay? If we look at 1 ohm and 5, we know that these two are connected in series. Okay, and they'll give us a 6 ohm equivalent resistance. Okay, then 6 and 3, they are connected in parallel. So using that R1 multiplied by R2 over R1 plus R2, it should give us 2 ohms here as the equivalent resistance of these two here. Okay, but then there's another resistor on top of this parallel combination, which is the 2 ohm. So now again, the equivalent resistance of these two then give us 4 ohm. If that's the case, then our circuit becomes 4 here, 4 there, 6 there, like that, and 8 there. Okay, so again, what is the equivalent resistance of these two resistors, 4 ohm and 6 ohm resistors connected in parallel? Again, it will be 4 times 6 over 10. This should give us, I think, 2.4 ohms, okay, as the equivalent resistance. So meaning we have now a circuit that uses 2, 4 there, 2.4 there, 8 there. So meaning, if you look into this circuit, REQ should be equal to 4 plus 2.4 plus 8, which should be, I think, this is what? 4 plus 8 is 12. 12, so I think it should be 14.4 ohms as the equivalent resistance for this circuit that is shown in figure 1.8. Okay, so if you go through the solution, I think you should be able to get the same answer. It's there, 14.1, 14.4 ohms as the equivalent resistance. Okay, I hope that is okay for everyone. If not, whenever you feel something is not clear, you always prompt me to try and
Yes,
clarify. Yes, yes.
are
Axon.
you able to go through the example? Just repeat again. I'm lost. I'm unable to
Where
follow. Especially starting
where
from the value of 6. Just go a bit up a bit. Yeah, there. Starting from 6. Where you got the 6.
starting
Yeah.
where I got, you mean where I got 6?
Yeah, the 6. The 6.
Okay.
On the same example.
Okay.
Yeah.
What I was saying is if you look at these resistors, there's 1 there and there's 5 here. How are these? Okay, let me, with respect to this point N and Q, how is 1 and 5 connected? That's your question, Axon. If you were to go like this, how is resistor 1 ohm and 5 ohm connected?
They're connected in series.
They're in series.
They're in series.
Yes. And we said resistors in series, what is their resistance? Equivalent resistance.
Just addition.
Just the addition of the individual resistances. Yes, Axon?
I'm there.
Remember? Yes,
Yes.
we had said that if you have R1, R2, R3, okay? The equivalent resistance of these resistors that are connected in series was REQ equal to R1 plus R2 plus R3. That's what we said. So we just applied that very expression on when 2 resistors are connected in parallel, whose resistances are 1 ohm and 5 ohm. That's what we said. Okay, I hope that's okay now.
Yeah, it's okay.
Okay. Okay. Okay. So that was the final answer there. Here's another question. 2.10. Asking us calculate the equivalent resistance AB. Okay, if you look at these terminals A and B there, okay, what equivalent resistance can you see? Okay, so here someone will say, no, but yeah, what and what? But I think if one understands what is happening here, can someone say what is happening there?
It's a loop.
There's a loop. What does it, okay, in short, I'm trying to get, what does it mean when you have a line that is drawn like that between from CB, from C to B, and from B to D. Across, when you have lines like that, what do you, let's say I have these two lines.
I think it means there is no connection between the two
No,
lines.
they're not meeting. They're not meeting.
Okay, so there's no connection. So meaning, for you to clearly see what is happening here, is you have to redraw this. Okay, so try to redraw this circuit. I think it should be something like this. We try to redraw the circuit to be able to get okay. We have a 10 there. Then down here we have a 3. Okay, so since we have said that there is no connection between this point, then what it means is, you remember this was B, and there is nothing sitting between this point and this point. So we can clearly see that this whole line is just nothing but the same point. Okay, so we can still say we have 3 there. Then it means, again, at the same point C, okay, we can say this is another point C. We can have the 6 here, 6 ohm, like that. Okay, because we know that it's connected to B. Again, we go there, we have a 1 ohm there. Okay, then we get to point D. Then again, at D, we have 2 resistors that are connected there in parallel. We have the 12. Okay, it's connected on the other end to B. Again, at the same D, we have the 4 connected also to B. Then there we have a 1, a 5, like that. This is what? This was 4. Okay, so if you redraw this circuit, this is how it should look like. And therefore, once you redraw and you can see now, I'm sure it's very clear to see like what is where. Then it tells us that we can see that this one, 1 and 5, they are in series. What we'll get is 6 ohms as their equivalent resistance. Then these two, 4 and 12, they are also in parallel. So what you get there will be 12 times 4 over 16. I think this is what? 12 times 4 divided by 16. 1, 2, 3, eh?
3.
Yeah, I think this should be 3. Okay.
12
And
plus 2.
also, come again. Okay. So, and also again, we have these 2 that are connected in parallel. These ones will give us 2 ohm. We've calculated that one already from the previous exam. Okay. So, one thing I need to tell you is that 6 and 12 are not in parallel. Okay. They are not in parallel because there is this 1 ohm that is sitting between C and D. If you look at the ones that we've considered to be in parallel, they are both connected to the same point. B and B, there is the same B. So C and C is the same point. Okay? But if someone was to say 6 and 12 are connected parallel, I would be very surprised because B and B are at the bottom terminals, yes, they are both connected to B. But 6 is connected to C and the other terminal of 12 is connected to D. So there's no way 6 and 12 can be in parallel. There is no way 10 and 3 ohms can be parallel because they are just connected at C. And you can't say that 10 and 3 are in series. No, because there is a branch now. There are other elements that are connected to C also. Okay? Unless if it was a case of 1 and 5 where there is no other branch between 5 and 1 there. That's when they are in series. Otherwise, you have to be careful when you are saying, okay, this one and this one are in series, this one and this one are in parallel. Okay, so if you did that correctly, then what you should have obtained would be a 10 there. Okay, you get to point C. Then here you have a 2 ohm. This is C. Then you have that 1 ohm. Then you get to D. And then you have another resistor there, which is what, 3. Okay, then you have, okay, so what I'll do is I'll just draw one since it's just the same. Anyway, it's the same thing. The same thing. So you have another one there like that. Okay, this is B, but this is what? This is 6 ohms now. Okay, so again, 6 and 3, they are connected in parallel because they are connected, both are connected to D and B. Okay, so 6 and 3, this one, they are in parallel because they are connected to D and B, both of them. Meaning the equivalent resistance is what? 2 ohm. Okay, and if that's the case, then your circuit reduces to 10 here, 1 there, then you have a 2 there. Okay, so now this one, there is point D there. It is C. This is B. Then you have a 2 ohm there. 1 ohm, 10 ohms, like that. Again, you see that this one and this 2, they are in series. They will give you the equivalent resistance of what? 3 ohms. And then now you realize that 3 ohms and 3 ohms are in parallel. Okay, and you remember the equivalent resistance of 2 means it will be the product, which is 9, divided by the sum, which is 6. Okay, which should give you, I think this should be 1.5 or so. Yeah, 1.5 ohms. Okay, so now you have this 1.5, meaning your circuit now reduces to what? To 10, you get to C, then you have 1.5, you get to B, you come back. This is point B, this is A. So if you look into this, what you get then, Req should be equal to 10 plus 1.5, which is equal to 11.5 ohms as the equivalent resistance. Okay, so you really have to, if the circuit is drawn in a certain way, you really have to try and see if you can manage to redraw like we did here, so that you can, as you redraw, make sure you try to identify the nodes themselves. If you see that there's something that is sitting between 2 nodes, then those elements can never be parallel because of that element between those 2 nodes. Okay, otherwise you can try to follow through the other solution to the example. I guess it will just still dictate to you the same thing. Oh,
Excuse me,
yeah.
sir.
Yes.
Oh, just a bit
Where
of
did I?
explanation. Yeah, just a bit of
Yes.
explanation on the why the 6 ohms and the 12 ohms are not in parallel. I kind of missed it there.
Okay. The 6, this 6 here and this 12 can never be in parallel because of between C and D. There is, remember we said that they must be connected to the same node. Both terminals have to be connected to the same point. So like if you look at 6 and 3, 3 and 6 on top, they are connected to C. And again, the other terminals of 6 and 3, they are connected to B. So they must be connected to the same point, in short. Otherwise, we can say it's like this. There's point C there. You have 3 there. And then you have 6 there. And they're both connected to these 2 points. It's like the way it is, C is there. And another B should be here at the bottom. Then this is 6. This is the only way they can be in parallel. But if they are connected to the same point on one end, on the other end, they are not connected to the same point, then that would fail. Are we together? Is that okay?
Yes, sir. Now, why wouldn't resistor number 1 and 5, which gave us a 6, why wouldn't it be in parallel? And yet,
The resistor number
1 and 1 ohm after the D and the 5, which gave us a 6. So it gave us they are in series, and yet resistor 3 and 6 are in parallel. Isn't this corner supposed to be one point where they are also connected?
Which one? This one. 1 and 5 is connected at this point. If you want to call this point E, right? But what is there? Where is the other terminal of 1 connected? It's connected to D. The other terminal of 5 is connected to B. But between D and B, there is this other element there. So they can't be in parallel. But in series, since there is nothing else that is connected at point E. When current flows, it has to come through 5 and come to B. Remember, the condition for parallel, for series, they must be exclusively be connected one node, and they must have the same current flowing to them. Right?
Yes, sir.
Yeah. Okay. If that's the case, I want to see where did they want to see. Okay, this one we are correct. That's okay. I want to see where the point 2 came from. I got 0.5. How come we have 0.2 here? Okay. This one, this one here. Okay. Okay, it comes to that. We said 12 and 4. Okay, is in parallel the 3 years. Then we had 5 and 6. Yeah, that were connected in parallel. So this one and that one. Okay. Oh yeah. Okay, I see it. Where did I say? Why did I say 3? Where did the 1.5 come from? We got it from. Oh, okay. I get it. So this is where we had made a mistake here. What we have here is that I think I forgot to write. This one is 2 here. I assumed it's 3. So this is a 2 ohm as the equivalent of 3 and 6. Then this one plus 2 gave us 3. So meaning the equivalent of this parallel combination should be 2 by 3 over 2 plus 3, which should be giving us 6 over 5. 6 over 5 gives you 1.2 there. Okay, to give you 1.2 at that point. So this is 1.2 ohm. And if you did that, then this one also changes. Instead of 1.5 becomes 1.2. Okay, so we have 1.2. Then this one gives us 11.2 ohms as the equivalent resistance. I had missed this point there. Okay, so that's how there's a step-by-step, but ultimately you should be able to get 11.2 ohms as the equivalent resistance. Okay, if that's okay, then There's another example here, example 2.11. Find the equivalent conductance for the circuit that is shown in figure 22A. If you look at this, they're asking us to find what GEQ is, okay? But then when you look at the circuit, you realize that from the circuit, resistor 8S and 12S, these two resistors are connected in parallel. Why? Because now we can see that they are both connected to this point, let's say A and B. The terminal of 8 is connected to A, and the other terminal of 12 is connected to A. The second terminal of 8 is connected to B, and the second terminal of 12 is connected to B. So these two are in parallel. And remember, when two resistors are connected in parallel, they are G, so 8 and 12. The equivalent conductance would be G8 plus G12, which is 8 plus 12 should give us 20. S. Okay, S, we say that this is the unit for conductance, which is Siemens or the mole. Okay, so if we have that, that as the equivalent resistance, conductance, then we can rewrite the circuit as the one shown in figure B. Okay, you have 6S there, we have the 5S on top, and this 20 comes from the parallel combination of 8 and 12. Okay, so from there we see that one terminal of 5S is connected to this point, let's say E. The other one is connected to, let's say, F. Then also the 20 is connected to F as well as to G. So you can see that if current was to flow in this E to F to G, then that current should be the same. And the fact that this current is the same and that these two conduct resistors 5 and 20 are connected at point F, okay, then we can say that they are in series. And if you remember, GEQ, 1 over GEQ for 5 and 20, we got 1 over 5 plus 1 over 20, okay, as the equivalent conductors. Then you can determine whatever that value is as the unit S. Okay, that value you get should be less than 5. Okay, so if you did that, then you should be able to get 4S. Okay, 4S is one less than 5. Okay, how? Okay, you can see, because we know that here the common, if you are to add these two, then we know that we have 20 here. 5 into 20 is 4. Okay, plus 20 20 is equal to 1. Then it clearly says the equivalent of conductances of 5 and 20 should be equal to 4S, which is the 4S that we have here. Okay, therefore, what we will end up having now is that 6S and 4S will be in parallel. So the circuit now reduces to 6S, okay, 4S. Then if you look into this circuit to find GEQ, then clearly says GEQ should be equal to 6 plus 4, which is equal to 10S, like that. Okay, so if you have this 10S, then you can also determine REQ from saying 1 over GEQ, which is equal to 1 over 10. It will give you that equivalent resistance would be equal to I think 0.1. Yeah, 0.1 ohms. Okay, so that's how you can do it if the values are given to you in terms of conductance. Otherwise, if you want, you can go through it. You can convert. If you don't want to deal with these conductances, you can convert the values into resistances as shown in this figure 22C. And then determine the equivalent resistance, then come and determine the equivalent conductance using the resistance method. Then you should be able to get the same answer, 10S. Okay, I hope that is fair for everyone. If that is okay, then there is this example also 2.12, which is asking us to say, for the circuit shown in this figure, determine the voltage V0, okay? The power supplied by the current source and the power absorbed by each resistor. Okay, so here, what we can do is, if we look at this circuit, we know that there is this, can even do KCL at point N, not N. We know that there will be this current flowing this side, there's this current going down, there's this current going like that. So you can say this is I0, then I1, I2, as shown in figure B. Okay, but then figure B has been rewritten such a way that if you look at the circuit of figure A, the 6 kilo ohm and the 12 kilo ohm, you would agree that they will have the same current flowing. And the fact that they are connected just the same node there, then they will have, they are connected in series. Okay, so you can quickly add 6 and 12 to get this 18 that you are seeing in figure B. Okay, so since you have that 18 in figure B, then what that tells us is that we can find the current I1 and I2. I2 flows through the 18 kilo ohm resistance and I1 flows through the 9K. Okay, we know the source, 30 milliamp. So if this is what I was trying to say then earlier, if you are to find I1, so I1 is equal to the equivalent resistance minus the resistance where that I1 is flowing through. It will give you 18K over the sum of all the resistances. Okay, so it will be over the sum of all the resistors that are available in that circuit. So it will be 18 plus 9 should give us, I think 18 plus 9 is what? 27? 27K multiplied by the 30 milliamp. Okay, so that's how you would determine I1. If you are to determine I2 first, I2 should be equal to exclude minus the resistance or where it's flowing. So you have 9 over 27, okay, multiplied by okay. And once we have that voltage V0, then we can determine the power that is supplied by the 30 milliamp, the power that is absorbed by the 18K We already know how that can be done. Is that clear?
Yes, sir.
Okay. I1, this is what I was trying to say. 18 over 9 plus 18, this is the one. When you add this, I think it should give you 27, somewhere there. Okay? So that, you get 10 milliamps. Okay? If you want, you can just use KCL. If you remember KCL at node N, it's 30, 30 milliamp equal to I1 plus I2, which I mean the 30 is the one who said I0. Like that. Then once you get to I1, then you can say I2 is equal to I0 minus I1. It will still work if you don't want to use the second current divider expression to determine I2. And then you know the VI, you can determine the power. So the power that is supplied by the current source is given by this, because we know that the current source and the 9K, actually all those elements are actually connected in parallel, all the three. So V0 is the voltage across the current source, is the voltage across the 9K, it's a voltage across the 18K. Okay, so they have the same voltage. So you see that the voltage here is the same for all of them. Okay, and once we have that, then you can quickly determine what the power that is supplied by each one of them. Okay. If I'll take you back to this circuit, the one we had to rewrite. Okay. If by any chance you find that this point is actually now connected, there is a connection there. What I mean is, if this 6 here and this 12, at the point where it was saying that there's no connection, it is connected. And maybe there's even another element here, another resistor there before you get to D. If this is connected and you have an element like this, which is 3 here, when you look at this 3, 6, 12, how are they connected? Can someone try to guess this? See
In
here.
series.
Okay, there's this point, I'll call this point P. 3, 6, 12. How are they connected?
They're in series.
Okay, look at the entire circuit. I'm still trying to redraw it. There's a 4 here. There's maybe another X there. Okay, even if I left it like this, you know. So if there's this resistor X there, there's this resistor Y there. So yeah, I was asked, if you look at this 3, 6, 12, how are they connected? How are they connected? I'm getting series. Hello?
Because of the presence of the other, because of the presence of the
Yeah,
other resistors connected to the same node there.
from P,
Yes, from P, there are others that have been connected. We may be afraid to say that they are in parallel.
Okay. Won't you be afraid also to say they are in series?
No, because of the other resistor. You see, there's the Y here, the resistor Y here.
Yes.
There's the resistor T. So these
Yes.
ones are connected in the same node. So if we tried to look at the examples you've given,
Yeah.
because if we say these three are in parallel, in series, then all of these then they're in series,
Okay.
which is not possible.
It's not possible. Okay. So in an event that that point is connected, the resistors 3 and 6, remember when it was not connected, that was in parallel. Okay. Or even if we have resistor 6 or the way of, but then if there was no at point P, there was no connection, then we would have just said 3 is in parallel to 6 plus T, right? Because there is no connection at point P. But if there is that connection, resistor 3, 6 cannot be considered to be in series. They cannot be considered to be in parallel. Okay? Yeah, I know they are connected at point C, but then because the fact that there is another 1 ohm between C and D, the current that will flow through 3 and the current that will flow through 6 will not be the same. Remember the condition for series? They must be connected to one node. Okay? Then it fails. Now, because we can have a situation like this, where we are looking at the resistors and we can see that they are neither in parallel nor in series. Then we bring this guy here. Y delta transformations. There will be a certain point where when you look at the resistors, the way they are connected, you can't see any series, you can't see any parallel. Then look out for these two again. Chances are high that they are either, if they are none of the parallel or series connection, then it's either they are connected in Y, which others books you find they are calling it star, okay? Or they are connected in dot. But now, if they are connected in Y or dot, and you are still trying to find the equivalent resistance, how can you do that? Okay, so this is what we are saying. If this fails, then you have to look out for the other. Okay, many circuits in nature can be simplified by using a 3-terminal network called the Y, others call it the T, okay, and delta, which others may refer to as the pi, okay. So you have to know also how you can determine the equivalent resistance whenever you find resistors connected in such a manner. Okay, so why you need to know this this transformation is that when you look at the circuit, just in case, for example, at A, there was another resistor there, okay, coming to B. But then this RC is not there. I don't know if you get what I mean. What I'm saying is, for example, if you have a circuit like this, you have a circuit like this, okay? They are connected there, they are connected there, and a circuit there. You have another resistor there. Okay, this is the same point. You have another resistor there. Okay, so if you have a network like this and then someone asks you to say, can you determine the equivalent resistance from this point? it will be very difficult for you to say, oh, okay, you will try by all means to say, maybe this one and this one are in parallel. A and B are in parallel, are in series. But you realize that because of this connection here, the currents in A and B will not be the same. And because of that other branch there. So you will not see that. But if you look at this circuit properly, you would realize that resistors, there's A, B, C, D, E, F. If you look at that, you can choose to say these resistors B, C, D, they are connected in Y. Okay, because we have B there, we have D there, we have C there. So if we can transform this Y into delta, like this, you would realize that the resistor that will sit there, and this one, and this one, they will form some parallel combination to here. We have F. Again, there we have E. Then there, this other side, you have A. So if you convert the B, C, D, Y into delta, it will give you H, I, J resistors. And then that's how the H, I, J, which will be connected in delta, will be connected with respect to these other resistors that you already have. Then you realize that H is in parallel to F, E is in parallel to J, A is in parallel with I. Then you know already how to do the parallel combination. And then you realize if you do the parallel of H and E, though these two will be in series. This one and that one will be in what? Series. And then you get the sum. Then the series equivalent will be in parallel to this one. Then you would have found the equivalent resistance. So from star to delta, it helps us because you need to change one to the other. Probably when you convert it to delta, the circuit becomes easier to analyze. Okay, so now how do you do that? If you are moving from delta, you you've identified the circuit that is connected in delta, and you want to convert it into star. We are calling it delta to Y or delta to star conversion. So you have the circuit that you have here that is connected in delta. It's RC, RA, RB. This is the delta connection. And then you want to convert this delta to the star, which is R1, R2, R3, like that. So convert this delta into that equivalent Y. How to do that is the denominator for these resistors when you are converting from delta to star is the same. Okay, so the denominator is the same. What will be differing is the numerator. So if you are to get R1, okay, you go to where R1 is connected to the delta. It's connected at point A. So we're trying to get R1. So R1 is connected at point A. Get the product of the two resistors that are sitting on the left and right of R1, but connected to point what? Point A. If you look at that, you will see that there's RB and RC. So the product of that RB, RC over the sum of those resistors that are connected in delta. RA, RB, RC. Okay? Also, if you come to determine what R2 is, R2 is connected to point B, to the delta. But what are those two resistors that are connected to B, that are in delta? We have RA, RC, divided by RA, RB, RC. Okay? Equally, you do the same for R3. That would give you, so R1 and R2, R3 would have been obtained as the equivalent resistance to the delta connection. Okay. I hope that is okay. Before we move to the white delta. Is that okay from what I've been saying here?
Yes, sir.
It's clear, sir.
Okay. So first things first, just determine the total sum of those resistors in series so that you have a common denominator, because I'm sure you can see from 2.1, 21, 22, 23, the denominator is the same. What is different is the numerator. Okay? But when we get to the y, you would realize that the numerator is the same. What is different is the denominator. Okay? So each resistor in the Y network is the product of the resistors in the adjacent delta divided by the sum of the three resistors in delta. So this one is just trying to conclude on the delta, the one who are saying that, oh, okay, it's a product of the delta that are connected to the same resistor divided by the sum of those resistors in delta. Okay, but if you are to consider now from what if you are given these resistors as R1, okay, R2, R3. Now you want to convert this to RA, RC, RB. So the numbering, how you name them or number them is up to you. But let's assume you have that connection in R1, R2, R3, and you want to move to get the equivalent connection as RA, RB, RC. So you can see that this one is the Y and this is the delta. Okay, so we are moving from star to delta. The numerator is the same. So the numerator of the Y is obtained as the sum of the what? The product of the resistors in what? In the Y. How is that? We are saying get the product, the sum of R1 multiplied by R2 plus R2 multiplied by R3 plus R3 multiplied by R1. Once you have this sum of products, then you'd have obtained your numerator. Okay? Therefore, if you have the numerator, what is the denominator? Okay? So, if you look at this circuit of figure 25, what we have here is this. what we have here is this. If you are to obtain, remember we are moving from R1, R2, R3. We want to go to RA, RB, RC. So the numerator, we already know it. Okay. It's the product, sum of products. R1, R2, R2, R3, R3, R4 divided by, okay. So if you are to get RA, the denominator should be the resistor that is sitting diametrically opposite to R1. Okay, if you are at RA here, what is the resistor that is, in short, what that is not connected at all to RA? You see that it's R1. So the denominator here will be R1. Christopher, you are clearing your throat. You want to say something?
No, you're right, sir. I left my I didn't mute my mic. Sorry, sir.
Oh, okay. Yeah. Okay. So let's try RB. If you want to find RB, we already know what the numerator is. But what is the denominator? RB is not connected at all to R2. That will be the denominator. Or we are saying that the denominator when determining RB is the resistor that when you look into the Y, the one that is directly opposite to RB. That's the denominator. So if you look at RB and direct opposite to RB on the Y, you have R2 there. That becomes the denominator. Equally, to get RC, the denominator should automatically be what? R3. But the numerator is the same. Like that. So you just have to, I don't know whether it's to Patira or to master or that you can do on this one. I have my own easy way to remember the equation when I'm moving from delta to star or star to delta. But most of the times you find that students, they switch the two. They are trying to move from delta to star, but they are using these expressions 24, 25, 26 when they are moving from delta to star. Okay? Or someone is trying to move from star to delta. They use the equations that we discussed in the previous slide. So I don't know how one, as an individual, how you can try to really pick these expressions so that you don't mix the two at all. Okay, but at least one hint that I know is that provided you are dividing by a single resistor, then you are moving from star to delta. Otherwise, the other one you are dividing by a sum of those individual resistors. So yeah, I think somewhere it's there, someone be able to obtain the to obtain or difference between delta to star and star to delta. Okay. So each resistor in the delta network is the sum of all the possible products. R1, R2 plus R2, R3 plus R3, R1 of the Y resistors taken two at a time. Okay, divided by the opposite Y resistor. The one I was saying, the one that appears diametrically opposite, or the one that is not actually connected at all to that very resistor. This is what this point is telling us. Otherwise, the Y and the delta networks are said to be balanced if we say that they are balanced, then we know that all the resistors are the same if the network is balanced. Then you would say that R1 is equal to R2 is equal to R3 for a RY. This will be the Y resistance, and therefore for the delta it will be RA, RB, RC being equal to R delta. So under these conditions of 2.27, the equivalent transformation, if you are to determine the resistance in Y given the R delta, you just divide by 3. Okay? Or if you have the star resistance, then to get the R delta, you just multiply it by 3. In short, the Y is 1/3 of the delta. If you are to transform from delta to star, given that the resistance are the same. Okay, so you can try to use also 2.28, given that the network is balanced. But it's very rare that someone will tell you that, oh, it's balanced. Realistically, the network, the systems are not balanced. Just that this assumption is there to lift certain ambiguities that one might go through when trying to actually analyze a certain circuit. Okay. So if we have that, then there's an example here. And quickly, okay, convert this delta, okay, convert this delta network. You remember it's connected at A, B, C. We have 25 connected in delta, 15, 10. They want us to obtain this Y. Okay. Actually, for you to know properly which one is which, yeah, I think it's to, when you put on your rough paper, you have to draw that delta and put a Y inside so that you can know which ones are the actual resistors that you are supposed to use. So if this is R1, this is my R2, this is my R3, I know what to do. R1 is equal to, remember, from delta to star, because I know where R1 is connected. It's connected to point A. It dictates that the numerator should be the product of two resistors that are connected to RA together with R1. I mean, that are connected at point A where R1 is connected. So I'll have RB multiplied by RC divided by RA plus RB plus RC. There. So if I look at what I've been given, I have RB as 10 multiplied by 25 over the denominator is 10 plus 25 plus 15. Okay. I don't know what this simplifies to. This is what 250. 250 over. This is 35.
Yes, sir.
I think 50. Yeah.
The
Like that.
whiteboard does not space, sir.
It has what?
The whiteboard has enough space, sir.
You want me to go to the whiteboard? But then I'll go and start copying this. Anyway, let me go to the whiteboard. Where is it? Where is the whiteboard? Where is the whiteboard? How do I get
It's
to the
better
whiteboard?
like this, analyzing it from here, the diagrams and everything. It's better like this.
Because if I go there, it means I have to draw. That's why I usually want to write just change the color.
You can proceed, sir. You can proceed.
Yeah. Okay. Okay. So if what I've done here, my multiplication and additions are correct. This is 250 as the numerator. And then the denominator is 10 plus 25, 35 plus 15. I think it's 50. So meaning it will give us R1 to be equal to 5 ohms. Okay. So we found one branch. The Y branch now is equal to 5. Okay, one of them that is connected to point A. Okay, so if we want to find R2, R2 again is equal to the R2 is connected to point B. Okay, so what are those two resistors that are in delta connected to B? It's RC multiplied by RA divided by 50. Okay, because we know that is the same. So it will be 25 multiplied by 15 divided by 50. So if you do your math properly from that, I think 25 multiplied by 15 is 375. If you divide this by 50, you should be able to get 7.5 ohms as R2. So again, you have that neutral point, then you have this as point B, then 7.5. Okay. Is this Y resistor that is connected to point C. So that one, again, if you come to point C there, you agree with me that R3 is equal to 15 times 10 over 50, which is 150 over 50 to give us 3 ohms. Okay, so we have a 3 ohms there. You want, you can put the units there. Okay, so that's how you would actually transform this delta connected network ABs, RC, RB, RA that are connected in delta into the equivalent star connected R1, R2, R3. Okay, any issues? Anyone who feels me there? Okay, silence means we are following or we are lost. Otherwise, yeah, this is how it was done one at a time, which we were trying to do on that on the actual question where we were writing. Okay, so that was for that example. Then or maybe sometimes someone is saying, oh, here's another example. Obtain the equivalent resistance RAB for the circuit shown in figure 27. Okay. When you obtain, so RAB from this circuit, RAB is here. You stand between these two. In short, if you disconnected the 120 voltage source, what is the equivalent resistance that you're going to see if you look into the circuit from here? Okay. So from there, it's saying that once you have RAB, calculate this current. Because what it tells you is that if you have RAB, then you can redraw your circuit to this. Okay. This is point B. This is point A. Then on the other side, you have RAB. Then you will see that there will be this current I flowing. This is 120 volts, like that. Okay, so given a question, someone says, oh, can you calculate the current I in this circuit? What they are just trying to tell you is, oh, okay, before you do that, because you will not say that I is equal to 120 over 12.5, 120 over 15, or 120 over 30. It's not possible. So meaning you first have to find what this REQ is, and then you redraw the circuit in the manner that I've shown here, and then calculate I as equal to 120 over RAB, like that. So now, for you to do that, you look, come and sit here. You look at 12.5 and 10. They are not in parallel. They are not in series. Okay. Again, you come and look at 15 and 12.5. They are not in series. 15 and 5. They are not in series. They are not in parallel. So you realize certainly to say, oh, okay, since I can't see any parallel for now, let me look for the other connections. Okay. You can look for the delta. You can look for the y. Okay. One person would choose to say, oh, okay, I can see. If I consider point N or point C, you choose which one you want to consider. But considering point N, the 5, the 10, the 20, they are connected in star. So you can put a delta like that. Okay, I will go around to avoid the numbers like that. Okay, one person will choose to do this. Okay, that's a, so you have to find now what is this, if you want to call them RA, RB, RC like that. Because you see that quickly, once you do that, you know that RB and 30, they're in parallel. Then you come and say also this other side, 15 and RC, they are in parallel. Then also this side, 12.5 is in parallel to RA. Okay.
Just for the sake of consistency, what I saw from the examples is that in this case, it's like the rule of the triangle. So the RB would actually be RC.
Which one?
I'm saying from the examples we got, it's like the rule of the triangle. So RB here would actually be RC. Then the RC will be RA. And then the yeah, so the RA, because there's RA, then RC, yeah, like that, yes, like that, yeah. From the example that you have given, it's like
Remember,
the finger
it's
there is opposite the other resistor.
oh, you want to follow because of the this C here to say the one opposite is the RC.
Yes, sir.
Okay, I see. Nah, otherwise you can use any. You can one person would call the one I've called RB, the RC. The other one can, how you name them, it doesn't matter. Provided you use the correct formula, it should come out. The triangle, because the position is commutative. Remember, you can still swap position and still be connected in delta. So there's no specific to say no, the delta should have the triangle RA should always be on the right side of the delta. I don't know. But as long as you name them correctly and you use the correct formula, I think what you should be able to get from them should be the same.
All right.
Okay, regardless of which one you might say, okay, this is my RA here. Then Jacob will come and say this is their RC. But if you calculate, you find that your RA and RC is the same. Then there's no problem. Even me, when I'm marking, I will not say, because I said that me, I said RA is this same one. Then I come and mark Jacob wrong because they've said RC is that. I know because of those choices that we have, I have to give as many options as possible so that I account for someone else who has used
Okay,
the
noted, sir.
different nomenclature. Yes.
Noted, sir.
Okay. Sharp. So if that's the case and you've assigned these values like the resistances like that, then the job now is to just determine RA, RB, RC, and then you go on and get that parallel equivalent. So if we try to do that, then if you look at, okay, I usually approaching the we put here. So many options here, actually. You look into this example, one person will not see this Y. Because me, I will not tell you to say, no, use convert that Y into delta. So it is no. I'll just say calculate I. So it's up to you how you simplify the equivalent resistance. It should be the same at the end of the day. So another person might see, if you look at this point A and B, this 10, this 20, and this 30. Can someone agree that they actually connected in delta? Hello?
Yes, sir.
So if they are connected in delta, someone again would want to come and calculate what this Y is. There, and also go there. Oh, so, and also calculate that that value of resistance there. Like that. Okay? So that whatever value of RA that you get from here, okay, not RA, but R1, okay, R1, R2, R3. You will see that R1 and 5, they will be in series. So you just add them, okay, to get one equivalent resistance there. But again, the challenge with changing the outer delta to Y, it will leave you with a situation like this. You have a 12 here, you have the equivalent of the 5 and R1, and then you have R3 there. Then you have a 12.5 here. So again, it will be, you have to start, because you can't say R3 and the 12.5 is in parallel because of this one. So you really have to make your choice strategic. Otherwise, you might be going in circles. Okay. So like this one, if you chose this outer one, the delta on the right to Y, it will force you to come and transform again from one way to the one way, whether from star or delta to star again. So you have to choose one, make the choice that when you do that transformation, they need to start giving you those series parallel kind of combination. Unless otherwise the circuit is just a bit complex that you still have to do other points in, you have to do them in star to delta transformation again. Okay, but otherwise, if we choose the approach of the star to delta at the points that I've selected to be in red, okay, then what we end up having should be something like this. Okay, it will be that. So if you go by the star to delta, then you realize that you have 25. So you can get the equivalent delta. So remember that product, any two products, but the sum, then you divide by the one that is opposite that. So it gives you RA to be 35. Okay. You come for the other one, RB, its denominator, the numerator is still the same 350. Okay. Divided by the one opposite or the one that is not connected, where RB is connected, to give you this. Go to RC, you get that. Then you can even draw your circuit now. So if you did that, remember, and then you have to remember where exactly the is there and the 35 is there. Because they didn't actually mark the point, the actual points, positions or points where those resistors were connected. And if you have values like this, then at the end of the day, the equivalent resistance that you get and the one that I'll get will be very different. Then me, I'll quickly wherever you are correct, but where you miss out, then I also hold my hand there. Okay, so if you did that, you'd realize that this 70 and 8 are actually in what? In parallel. So you can obtain that parallel combination. So these two are in parallel. Okay, these two are in parallel. Okay, because they are both here and there. These two also are in parallel. These two also are in parallel. If you want, you can redraw this circuit. Please see that they are in parallel. So parallel, parallel, and then whatever you get from this parallel combination should be in series to this. And that series combination should be in parallel to whatever comes out from there. So if you followed the 15 and the 35 in parallel, give you this. The 12.5 and okay, these two are in series, you can add them. Whatever result you get, it's in parallel to the 20. And you can go ahead like that and get the RAB. Once you have RAB, then calculating the current, it's even much simpler now. Okay. Otherwise, another person would have opted instead of the one that had drawn in blue. Someone would have delta from 12.5, 5, and 10. They are connected in delta. So someone would want to say, okay, me, I'll get this Y there. It comes the other side. And then you have also another resistor coming. So when you obtain that, you'd realize that this one and the 15, they will be in series. This one and the 20 will be in series. Okay? So once you have that, then it will force you to come and have this circuit. This is the circuit that you have. If you converted the 12.5, the 5, and 10, that is connected in delta there from where I'm just from drawing, it will give you a circuit like this as the next simplified circuit. Then the ones that I was saying, series to 15, it is these two are in series, these two are in series. Once you solve this series combination, they are connected in parallel. Parallel combination connects in series to this one. Then when you have that equivalent again, it will be parallel to the third there. Okay, so unless otherwise, it was just an example which you can go through, sit down properly, can play around the transformations, see which one you are very familiar with. Probably if you become conversant with one, then I would say every time you have a circuit, try and find the one that gives you the simplest transformation that you can remember and see how it simplifies the equivalent, the next equivalent circuit. Okay. Yeah, otherwise this was just, if you opted for the other, then you should have ran through and arrive at RAB is equal to 9.632. Then the current that they're asking is VS over RAB, 120 over that to give you 4 point something amps as the current. Okay, so yeah, we can evaluate problem using delta to start transformation. Okay, so this one, it's just remember we said that if one chose the Y to delta. Then the second person might have chosen the delta to y. Then I was 2.55 and 10. You take them to y. If you solve, you should be able to come and arrive at the same, the equivalent resistance will be the same. Thus, even the, even the current that you calculate from that, from the two people. One, you transformed the y to delta, the other one transformed the delta to y. At the end of the day, the equivalent resistance would be the same, and the value of the current that you calculate there should be the same. If they are not the same, then one of the two didn't do something correctly. Any reactions? I've come to the end of today's class. Yeah. Hello? Me, I'm done.
Thank you,
For
sir.
today.
Thank you so much, sir.
We just need to go through.
Yeah.
And then I want, do you have any videos on lecture one?
No. Lecture one, I think I didn't have. Or I've forgotten how when we started recording, but there was a lecture that we taught. I think I was using Zoom. The one that I shared when we had when I was using Google Meet, there's no recording for those. The recording started coming after I started using the Zoom itself. So I think I've uploaded about 9, it should be 9 videos for the past 3 sessions. Last week, the other week, and the other week. Because you remember Zoom was cutting at in 40-40. So you find that at the end of the class, we would have had 3 recordings. So 3 recordings by 3 classes, I think there should be 9 of them. Part of one is on recording, the other part is not there. And remember, no. Yeah, part of one, because remember, I wasn't the one that started with you. My colleague started the class for me. So I don't know if Mr. Mwamba shared the recording that he had for the first part, but the first time I took over the class, I didn't record for that class. But the next one, I think we started recording. Yeah?
So how about the previous one before this one?
Before today's class, they are there on. There's a link that I shared. I usually just keep updating there. So if you want to see, when you go to that link that I shared, for the very first time I shared the videos, there's a link that I put there. I created a folder. So when I finish class like today, if I was the one recording, I would just go to that folder, upload those videos there. So the link, if someone opened the link today, they should see about 9 videos on that link.
Okay, thank you,
Yeah,
sir. Now,
sure.
sorry, sir. During sorry, when I was asking the question, my network had cut. I was asking about the GN, the one which you're writing at the far end of the formula. I didn't understand how what you meant by that GN, something like that. Just a clarification on that.
Okay. So BN, if remember we are starting to say G1 plus G2 plus G3. So like this. This is a general expression to say if you have resistors, a certain number of resistors that are connected in parallel, their conductances, the equivalent conductance of those are can be determined by this. So this is just the nth conductance. It's like you have At one point you have 100 resistors, the next time you have 10 resistors, another you have 1,000,000. So because we don't know, I don't want to give you to say they for 4 resistors that are connected in parallel, the equivalent conductance is this. Then someone will say, but what is the equivalent conductance of 100 resistors that are connected in parallel? So this is a general expression. N is any number for a given number. So the n is up to you. You can choose 4, 1 or 10, 1 will be at a median. But otherwise, no matter how many number of resistors that are connected in parallel, their conductances can be added to obtain the equivalent conductance like that.
Oh, okay, thank you. It's clear now.
Okay, sure. I think even the circuit, there should have been a circuit where it was showing, where it was trying to, where was that? Okay. This was for series. Okay. Okay. In short, it's like what we're trying to do here. They say you have G1, G2, G3. You don't know how many are here, but you know up to this one there, Gn. They could be G4, G5, G7, up to G100. These are connected in parallel. So in short, it just accounts like more like the way you did in chemistry, where I have the empirical formula. It gives you shorthand, but for you to know the actual formula, the molecular formula, start counting. Now you have to count how many carbons do you have. Then you just go and plug in there in the formula. Yeah, it should be something like like a circuit that I've drawn here. That's what. So n is just any number, no number. So you can it's up to determine how many resistors it is. Actually, it's even here for any number of resistors. Okay, then you can calculate your conductance like that. Okay. Otherwise, thank you so much. We've come to the end of today's class. We will see if we can do again next week, Monday. So the way I'll do it, you guys, since you are very far, the test that you write will be online. Are we together?
Yes, sir.
Yes, sir.
And that test will end up to where we'll end in the next 2 sittings for the next class. So when we start lecture 3 on Monday, so the next 2 Mondays, I know that other Monday is a holiday, but I think we can have the class because we don't have time on our side. At least by the time we have class, means Easter Monday has ended. Can we have the class?
Yes, sir.
Yes, sir.
Okay. So the class that we will have on Easter Monday, when where we'll end on Easter Monday's class, that's where the test will end. So I will try by all means to break down the questions so that because I will not be the one to mark, it will be the computer that will mark. So when I say to 4 decimal places, I try to account for a lot of factors. Someone rounding off at that level, someone rounding, even someone who doesn't round off at all. I know our calculators have memory. So someone will do this calculation, save the memory, they just recall that answer whenever until they get the final answer. So I'll have that. But if I do that, then someone rounds off here, there, and whatever. Then when the computer marks, provided someone gives the answer that's not amongst the options that are put, it will mark that wrong. So I'll try if I can find time somewhere this week or over the weekend. I'll try to set up more like a quiz online so that people can
sir.
have a feel of how that. Yes?
Yes, I have a question.
Yes.
Concerning what you've explained about marking.
Yes.
So which means you only mark the answers, not the proceed.
It's not me marking, it's a computer. It's AI, sir. Yeah, because if I wait to say until when you come back, come and write, you might want to write 2 tests because then my colleague will have to give you another test. So you can't come and write 2 tests in the second half when you come for residential. That's why we try to just give you open book. Then by the time you come, you've written a test, or you would have even written both tests. Then you are good. Yeah. Okay. All right. Thank you, guys. We'll see you again next week, man. Since we are done with